Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 9th, 2025, just 2 days ago. This paper introduces a method that achieves a massive 47 times speedup for 3D open vocabulary text querying. The paper is titled LangSplatV2, High-Dimensional 3D Language Gaussian Splatting with 450 plus FPS. And as we'll see, this makes real-time language interaction within complex 3D scenes a practical reality. It tackles a key performance bottleneck by eliminating a slow decoder with a new sparse coding approach. Also, the authors shared their official implementation on GitHub, and it's quite comprehensive. If you check it out, you'll find all the code for training and evaluation, along with data preprocessing scripts. They also provide links to the datasets and pre-trained models to help you get started right away. Alright, to really see the impact of this new method, the first figure provides a great visual. It plots rendering time against what's called the feature dimension, which is essentially the complexity of the language data being processed. The dashed lines show the original LangSplat, and you can see its rendering time just explodes as the features get more complex. In contrast, the solid lines for LangSplatV2 are nearly flat, staying incredibly fast and stable across different GPUs. This really drives home how the new sparse coding approach makes rendering almost independent of feature complexity. Digging into the numbers, this table breaks down exactly where those performance gains come from. It shows the time cost for each stage of the process. For the original LangSplat, you can see the huge bottleneck was the decoding step, taking a massive 83.1 milliseconds. This decoding is where the model translates compressed data back into complex language features. But with LangSplatV2, that decoding time is virtually eliminated, dropping to just 0.1 milliseconds. This single change drives the total query time down to an amazing 2.6 milliseconds, achieving that final speed of 384 frames per second. So, this next figure shows the new framework and exactly how they got rid of that slow decoder. On the left, you have the 3D Gaussians, which are the basic building blocks that represent the scene. Instead of attaching a complex feature to each one, the model learns what's called a sparse coefficient. This is just a simple set of weights for each Gaussian, where most of the values are 0. These weights are then combined with a shared global codebook. Think of it like a dictionary of feature patterns to reconstruct the final language map. This new approach is what makes the process so incredibly fast. Building on that new framework, the big question is, did all this speed come at the cost of accuracy? Well, this table answers that with a resounding no. It shows results for 3D semantic segmentation on the 3DOVS dataset. The scores are reported as mean intersection over union, which is a measure of how accurately the model identifies objects in the scene. A higher percentage is better. And as you can see, LangSplatV2 at the bottom achieves the highest overall score of 94.6%, outperforming not just the original LangSplat, but all other competing methods. And those better scores aren't just abstract numbers. This next set of images gives us a great visual comparison for what's called open vocabulary 3D object localization, which is basically asking the model to find an object in a scene just by typing in its name. For example, when searching for pumpkin or kamaboko, you can see the original LangSplat often creates a vague, diffuse highlight. In contrast, LangSplatV2 is much sharper, precisely identifying the object with a tight, accurate heat map. This visual evidence really confirms the quantitative improvements we just saw. To break down exactly where these speed gains come from, this table shows an ablation study on the LERF dataset. An ablation study is where researchers test a system by adding new components one by one to see how each part contributes. You can see that the original decode time was a massive 83.1 milliseconds. Just adding the sparse coefficient field, that new framework we saw drops the decode time to a negligible 0.1 milliseconds. Then, adding efficient splatting with CUDA optimization brings the final total query time down to a blistering 2.1 milliseconds. Alright, so to wrap things up, the main takeaway is that LangSplatV2 successfully solves the real-time performance bottleneck of its predecessor. By replacing the slow decoder, which was a type of network called a multi-layer perceptron. With a much more efficient sparse coefficient field and a global codebook, the authors achieved a massive speedup of over 40 times. And what's truly impressive is that this huge gain in speed also came with better accuracy. This work really opens the door for truly interactive language queries within complex 3D scenes.